we are going to look with a little more elaborate details about an example which we discussed in one of the lectures on differential calculus on several variables. Okay, and this is the kind of examples one should do instead of simply computing Jacobian del f by del x j etc. Okay, that gives you some more confidence, and when you go for higher studies like differential manifold geometry and or very high level theoretical physics, this kind of things will help you to understand and work with confidence. Okay, so let us get started. Yeah, so there will be an article on this with the same title. I'm yet to finish it and upload it. After this lecture I will do that. Okay, and if you want you can download it from there later. Okay, so let us quickly recall. So suppose I have vector spaces v1, v2 and w, all vector spaces over some field. Okay, for us usually it's R. Then a map f from v1 cross v2 to w is bilinear. Okay, if what do you have? So you notice that it has to be function of two variables, x in v1, y in v2, right? Therefore what do I have is, you fix y in v2, let's look at x going to f of xy. This is a map from v1 to w. This must be a linear map. And similarly fix x in v1 and let's look at y going to f of xy, and that's going to be a map from v2 to w. This must also be linear. So in each of the variables it's linear. That's it. Then we call this as a bilinear map. Yeah, right. Now a question. Do you know how to define v1 to vk to w, a k-linear map? Of course v1 to vk are really vector spaces over the same field. W is also vector space over the same field. How to define? Okay, I will be asking this kind of questions on the way, because whatever we are going to do is for bilinear, so that the ideas are very clear. Notation is not very complicated or involved. Okay, but whatever I'm going to do can be extended to multilinear maps also, and such maps are called multilinear. Bilinear, trilinear or k-linear, all are called multilinear maps. Okay, right. Okay, so this is just a question for your introspection and thing. Okay, so pause, review and proceed. Okay, right. Now naturally I would like to have some examples. The simplest example is a multiplication map on R. So hereafter we will take the field to be R. We will be dealing with finite dimensional vector space over R. Okay, multiplication map from R cross R to R. So v1 equal to v2 equal to R, w equal to R. What is the map? The xy going to x times y. This is a bilinear map. Okay, that's what actually your distributive law says. Okay, from that it follows, and of course associative also. This is the first example, and second example is what you already know when you are introduced inner product spaces. Okay, as usual we will look at inner product space over R. Suppose b cross b is a real inner product space. Okay, then I have an inner product. I usually denote by this, or you can also denote by dot product if you want Rn to cross Rn. So I have xy that goes to x dot y, the standard dot product. This is an inner product. Okay, so this map is also bilinear. Okay, some of the axioms, properties of the inner product, it clearly shows that they are bilinear. Okay, I don't want to spend time on such things. I'm sure all of you must have seen that. A third example is what we are going to concentrate most on in today's lecture. Okay, I would like you to learn this much better. So what I'm going to do is I'm going to look at M2R, that is 2 by 2 real matrices. Okay, now I want to define, see, first notice that if I have A, I will write it as A, B, C, D, A here. Okay, I may also write it as X, Y, Z, W if necessary. Okay, what I want to look at is I want to look at A as a pair of ordered pair of complex column vector, that is AC, this is first vector, and BD, this is second vector. So call this as C1 and C2, first column C1, second column. Therefore A is pair of two vectors. Therefore I can think of this as a vector in R2 cross R2. Remember, I always think of Rn as column vectors. Okay, I can think of this any matrix as an element of R2. Is that clear to you? Yeah, you can also think of as a row vector, that is AB is the first row, CD is the second row. Then in that case I will call it as R1, R2. Okay, anyway, so I can also think of this as a column. Okay, now what is the map I want? The map I want to think of is f of A equal to determinant of A. That is, I want to think of determinant of A as a function of two variables C1 and C2. Okay, right? And the properties of determinant say F is bilinear. Okay, see, if you read my linear algebra book, you would be very, very confident about such things. Otherwise, you may have to take a little time and review it. What does it mean? Suppose I have something like A, B, C, D. Okay, I add another vector. Okay, A plus X and C plus Y and BD. That is, I am adding C1 plus C1 dash, where C1 is this. C1 is AC and C2 is XY. C1 dash is XY. Then the properties of determinant says that it is linear. Okay, in each other variables. Okay, please check. Don't take it for granted. If this is the first time you are looking at determinant in this way, okay, please spend a few minutes, check it, and then come. Okay, do not just assume it should be all right. Okay, please do that. So this is a bilinear map. Okay, so what does that mean? This means f of C1 plus C1 dash C2 equal to f of C1 C2 plus f of C1 dash C2 and so on. And similarly C2 plus C2 dash, and then scalar, if I multiply C1 by alpha 1, that is the scalar alpha 1 comes out, etc, etc, etc. You should know what you have to check. Okay, do not assume, please do not assume. Okay, pause the video, check for 2 minutes and then come back. Okay, so now we are given 3 examples. As I said, the third example is what we are going to focus upon today, because the first 2 examples were already done in the earlier classes, and now in my video lectures on differential calculus on several variables. Okay, now what I want to do, the first thing I want to notice is something to dispose of. See, if F is a linear map from a vector space B to W, okay, suppose B is a basis of B, then if I know f of x for every x in B, then I know then f is completely determined. What do I mean by that? All of you know that if you want to assume V is finite dimensional, therefore given any vector B, I can write it as summation xi vi, where vi, okay, forms a basis B. Okay, assume I equal to 1 to n, etc, etc. Then what is f of B? Remember, f is linear, therefore I know this is summation xi f of vi. But I know what is f of vi, and since I know how to write B equal to summation xi vi, that means I know f of B. That's what we mean. Okay, this is linear algebra, you should be sure of such things. So natural question I can ask is, if f is a bilinear map from V1 V2 to W, okay, is there any analog of this? Is the question clear? Just think about for 10 seconds. Analog of what? That is, if I know F's action on something, ordered pairs of some elements, then I know F completely. That's what I want to know. I'm sure all of you know, since F is linear in each other variable, what is obvious guess? Obvious guess is, okay, for simplicity, again let me assume B1 equal to B2 equal to B, therefore let me assume this one. Okay, so for simplicity. But what I'm going to say is more general, true. Suppose I have a basis B equal to V1 to Vn of del B, right? Then what you would like to check, show, claim? Come on, all of you should try. What you would like to claim? If I know f of Vi, Vj for all I and j implies I know f. Okay. Do you understand this? Why? Suppose I start with two vectors x and y in V, then I can write x equal to summation xi vi, y equal to summation yj vj. I am right j equal to 1 to n, the same index, but you know the reason why we want to do. Okay, therefore what is f of xy? That is going to be f of summation xi vi. I am not going to write I equal to 1 to something, yj vj. Yeah, so first thing is, what do I know? Because of linearity in the first variable, right, this is going to be summation over I xi of f of vi and summation yj vj. I am using only linearity in the first variable. You understand that? For example, x1 plus v1. Okay, if you want to think of it v1 plus v2, that will be f of v1 summation yj vj plus f of v2 summation yj vj, and scalar also comes out. Do all of you understand this? Right. But now I can use linearity in the second variable. Yeah. So what do I get? Using linearity in the second variable, this is same as I xi and summation f of vi vj and yj comes out. Yj comes out, sorry, here yj comes out. Yeah, you understand this? Because this will be summation will come out for this. This is what I am writing. Yeah, but this I can write as summation xi yj, I and j both very independently from I equal to 1 to n, j equal to 1 to n of f of vi vj. Right? So like as we concluded in a linear case, what do I know? Once I know f of vi vj for all I and j, since I know how to write x equal to as a linear combination of vi, y equal to as a linear combination of vi, okay, I know what are xi and yi. Therefore I know this, the right hand side is completely known, and then the left hand side fxy is completely known. Do you understand this? Okay, pause, review, proceed. Okay, now comes the important thing. Now so far it's pure algebra in some sense. Okay, now I want to put an analysis. So what do we do is, I will let me take b equal to rm, w equal to rn if you want it. In fact, finally I will take w equal to r, but anyway, right? And notice that on rm and rn I have the norms. Okay, either Euclidean norm, okay, which comes from a dot product, or the maximum, which is modulus xi maximum, or summation norm mod xi, any one of the norms. Okay, it could be any norm, because if you know some topology, you know all norms are equivalent, but let's not worry about such things. I don't want to get digressed. Okay, fix one of the norms, either Euclidean norm or max norm. Okay, that's good enough for us. Yeah, but we are going to deal with only Euclidean norm, because you will see the reason. Okay, right. So what is that I know? Now therefore, suppose f from b cross b, that is rm cross rm to rn, is bilinear. Okay, I want to know whether it's continuous. Is the question clear? Yeah, why I can ask? Because rm has a metric, namely coming from the inner product. Okay, similarly Rm as a metric, therefore I have a product metric on this space, therefore I can and Rn as a metric, therefore I can ask whether continuity of this map. Do you understand this? Okay, the proof is again easy, the same way we proved the continuity of linear maps. Again in several variable calculus, second lecture I would have proved it. Okay, exactly the same proof is what I am going to adapt here. Okay, so what do you do is, let's keeping the above notation. Okay, let us look at E1 to EM, the standard basis, standard orthogonal basis, right, of Rm. Therefore f of x comma y is going to be summation xi yj f of ei ej ij vary. Is that clear? Yeah, right. How did I prove continuity of a linear map? I proved that f of x, the norm will be less than or equal to c times the norm of x. There exists a constant c, so that this happens for every x in Rm. If f is a linear map from Rm to Rn. Okay, this is not this bilinear map, this is just f from Rm to Rn. Okay, this is why I proved continuity. So similarly I want to prove f of xy norm will be less than or equal to some constant times the norm of xy. Okay, remember the ordered pair xy, where does it live? It lives in Rm cross Rm, so I have to find it. So aim is whether I have an analog of this. That's a question. I do not know whether it is true or not, but we are going to do that. Yeah, but that's very easy. Let's look at this. Therefore I have an obvious estimate for this. Mod xi mod yj into norm of f of ei ej. Yeah, how many such elements are there? N squared elements. They are finitely many, therefore I have an obvious constant. Yeah, so these are bounded by some constant, right? So let us assume this is less than or equal to some m for all ing. Therefore this is less than or equal to some m times summation mod xi into mod yj. Yeah, okay, but remember this is actually equal less than or equal to m into, all of you know mod xi is less than or equal to norm x, and similarly mod yi is less than or equal to yj is less than or equal to mod y, norm y. Right, this is for any one of the Euclidean norm, max norm or summation norm. We had already seen this. Do you follow that? Yeah, therefore I can replace this by norm of x into norm of y, right? But remember, what is the relation between norm of x? See, let us look at the vector x comma 0. Yeah, what is norm of x comma y, and what is the relation between norm of x and this? That's a question. Do you understand? Because remember, what is my aim? I want to replace it by, where did I say some norm of the ordered pair xy. But that's very easy, because what is your norm on the Rn cross Rn? That's again going to be summation xi squared plus summation yj squared and the whole thing to the power half. You understand that? Therefore if I wanted, I could replace everything by norm of pair xy, norm of pair xy. Do you understand this? Each one of the term mod xi will be less than or equal to this, but this is norm of xy. Do you follow that? And similarly mod yj also will be less than xi. Mod yj also will be less than or equal to norm of the ordered pair xy. Therefore there are two things, therefore less than or equal to. And how many such things are there? For each I n j, therefore n squared thing. Therefore this is equal, less than or equal to m into n squared into norm of x y whole squared. Yeah, so that's your constant. Yeah, okay, I hope I'm right. Okay. I don't like the square term here, but anyway, for the time being, I think I have not made any mistake. Let us just accept it. If there is any problem, we'll come back. Okay, so does this prove continuity? Yeah, because why does it prove continuity? Suppose I have f of x plus h, y plus k minus f of xy. Okay, I have to estimate this. Okay, now I leave it to you to check. Okay, using this kind of thing you can check continuity. Okay, so pause, review, proceed. Okay, right. Next question we want to know is the following. Let F again from Rm cross Rm to Rn bilinear. We already checked it is continuous, but you want to know whether it is differentiable. Yeah, you understand the question? Yeah. So let us fix. Okay, a comma or u comma v in Rm cross Rn. I want to know whether it is differentiable. So what does that mean? Remember, that is, take some increment hk, that is in Rm cross Rn. Therefore f of u plus h v plus k minus f of uv. This is what we want to do. We will have to approximate it by means of what? A linear map acting on the increment hk, and plus some error term which goes to 0 faster than the increment going to 0. All these things we know that, right? Keep that goal in mind so that you know how we are kind of manipulating or arranging terms so that we get it. Okay, right. Now what is f of u plus h? This is nothing other than, remember, it is f of u plus h will be f of u v plus k plus f of h v plus k minus f of uv. But this again I can write it f of uv plus f of uk plus f of hv plus f of hk minus f of u. Yeah, just think of as a bilinear map as a multiplication distributive law. Okay, you will get it. Okay, that's how I do fast. I think of this u into v plus k, therefore it is uv uk. That's it. And this is h into v plus k, that is hv hk. Yeah, so these get cancelled. Now what is our trick? Our trick is to find terms which are linear in the increment in the independent variable. So what are they? Only these two things, and this is second order. You see that? Therefore what do I think? I want to define d of, this is a candidate, we do not know whether it will work, so I want to define the derivative to be f of uk plus f of hv. You understand? So this is a linear, one can check. Yeah, because if I write h1 plus h2, this is going to be f of h1 plus h2 by bilinearity of f, that will be f of h1 h2 etc etc. Okay, please check. This kind of thing, you know, they are very trivial algebraic manipulations, checking, verification, you should do it. Okay, don't take it for granted. Okay, the way you can become confident is to do this kind of very trivial checkings. Okay, therefore if this is the one, what is my error term here? EHK. EHK is, that is f of u plus h v plus k minus f of uv minus this object. Therefore what is left out? F of hk. Yeah, therefore what is this now? The norm of this, we already have a bound. This is less than or equal to norm of hk whole squared. Just now we found it. Do you remember? Therefore limit hk goes to 0 of ehk by norm of hk is less than or equal to C of norm of hk. Limit hk goes to 0, which is 0. Yeah, do you understand that? So what have we shown? We have proved that f is differentiable and you have computed the derivative. Remember, we had already done it for dot product. Our first example was x going to x dot x. Do you remember that? And one of the later examples are multiplication. Both are special cases of this. Okay, so let us record the thing. So what do I have? Derivative of f at the point uv acting on hk is f of uk plus f of hv. Do you understand this? So we have found out the derivative. Please check. Okay, if you have your notes or if you have done earlier thing, okay, check. Okay, this tallies with the dot product map and multiplication on R. In fact, multiplication R is also dot product when n equal to 1. Yeah, so it's not anything special. Yeah, are you through now? Good. Now we want to apply this to our third example. What is the third example? We saw that the determinant map, let me call it F, from M to R, I can think of this as a map as what? A equal to column vector C1, C2, that going to determinant of C1, C2. This is bilinear. Therefore, I know this map F is differentiable. Yes. Therefore, this is a bilinear map. Therefore, it's differentiable. Therefore, if A equal to, let us say, A, B, C, D, and my increment H is X, Y, Z, W, okay, then I know what is D of A acting on H. Okay, don't get confused. This is C1, this is C2, this is H1, H2, column 1, column 2. You understand that? Therefore, if you want, this is your U, this is your V, this is your H, this is your K, keeping the earlier notation. Therefore, what is the derivative? This is D of A acting on H is determinant of U acting on K, that is C1 H2 plus you understand, F of U K. You right? What is U? My C1. What is K? That is my H2. And what is F? Is determinant. Okay, I will not repeat similar argument. Now it should be clear. This is going to be H1 and C2. Yeah, right, HKV, right. You follow that? But that's very easy to compute. What is this? This is determinant of A, C, Y, W plus determinant of H1, that is X, Z and BD. Just make sure I'm writing it correctly, because I'm more worried about explaining. Okay, so sometimes I make mistakes in computations. So what is this? This is AW minus CY plus DX minus BZ. Remember, F is a map from where to where? Bilinear map in R, right? Therefore, the derivative should be a map from where to where? It must be a linear map. Remember, it's a function. Okay, don't worry about bilinearity. Please concentrate. My F is a map from this vector space. Which is the vector space? R2 to R, which is M to R. To R. Therefore, the derivative at any point must be a linear map from R2 cross R2 to R. This must be just a linear map. Or it should be a linear map from M to R to R. if I consider any element as set of two ordered pair of column vectors C1 and C2. Do you understand? Please pay attention. Don't expect my f to be bilinear, the derivative of f to be bilinear, since f is bilinear. No. Okay, because when you are learning certain things, you unnecessarily get confused. Okay, that's why I'm explaining. Is that all right? Okay. So we have found out how does the derivative act on that. But remember, there is something I can do much better than this. Okay. Here, just as a digression, suppose f is a function from Rn to R and differentiable, okay, at A, then dfa acting on H, okay, therefore dfa will be linear functional from Rn to R. It's a linear. But then we know this is nothing other than something like gradient of f at A dot H. Yeah, there is a unique vector in Rn, so that the dot product of that vector with H is the map. So any linear function I can describe in terms of the gradient vector, linear function from Rn to R, right? Okay, so I can wonder, let's look at M to R. Okay, this is also something like R4, right? So I would like to know whether I can find some kind of a gradient. Yeah, but remember, how did I compute that gradient? See that this kind of example will make you review and revise the basic concepts very well. Otherwise you think you understood, so you just rush through. To do this, what did we do? This is a linear function just because Rn has an inner product. Okay, therefore any linear function phi from Rn to R is of the form phi of x equal to x dot b for a unique vector b. Okay, we need an inner product to compute that. You follow that? There is also another way we compute it, but I would like to put an inner product on R2, sorry, on M2R. Okay, that's very easy. Suppose I have A equal to ABCD, okay, right, and let us say another B equal to something like XYZW. Then I can identify this with X, A, B, C, D, and this with X, Y, Z, W in that order. Therefore the dot product I can say A dot B, that is inner product AB, equal to AX plus BY plus CZ plus DW as vectors ordered by, okay, quadruples in R4. You understand this? But then this is the way you identify. You could also identify with A, C, A, C, B, D, or in any fashion. But we just went by first row followed by second row and again from left to right fashion. Okay, top to bottom and each row left to right. With that identification we did that. But the very interesting thing is there is an intrinsic definition. Definition of this inner product, which involves notions related to matrices. Okay, these are the things which will make you confident of higher level mathematics. Okay, what is that? The thing is, I claim, you know, this inner product is nothing other than look at the trace of the element A into B transpose. See, what is A into B transpose? B is given, B transpose is another matrix. A times B transpose is a matrix multiplication. Trace of the matrix we know. You see that? All the things involved nothing to do with the way you identify A with a vector in R4. That's the crux of the matter. Do you understand that? That is why I call it intrinsic. Here this inner product depended upon how I identified the vector A with an ordered quadruple in R4. Okay, instead of ABCD I could also have done ADBC or ABCD or ACBD or ACDB, whatever way you want. Okay, but depending upon that, this inner product may also differ, but here it is different. Okay, right. This is intrinsic, right? Would you like to check it? It is very easy. It is A B C D into B transposes X and Y, therefore Z Y W. Therefore look at this, I want only the trace, that means I want only the diagonal element, that is AX plus BY and CZ plus DW. Therefore the trace is going to be sum of these things, AX plus BY, CZ plus DW. You understand that? I don't care what happens here. Okay, therefore trace of this is what we wrote. Have you understood this? Pause, review, proceed. Right? Okay. Yeah. Now I forgot, here we did for bilinear map. So as a next question, is such a formula is true for multilinear map, that is k-linear map? Are they differentiable? And next, such formula exist. Can you identify the formula? That's a question for you for exploration and investigation. If you are worried about too many notations, just to think of 3 by 3 trilinear if you want. Okay, and similarly you get, and notice that again I define inner product on M2R. Next question you can ask is, can I define inner product on MNR, n cross n square matrices? The obvious thing will be again A11, A12, A1n followed by A21, A2n followed by AN1, ANN. So the matrix A goes to ordered n squared tuple, and therefore I can identify with Rn squared, therefore I have a dot product, natural. Okay, but then with the, it depends on the identification. But again, can you have an intrinsic definition like this? Okay, these are all very trivial exercise. Okay, explore for exercise or question. Explore such things for MNR. These are later. Okay, do not stop here. This is for later investigation, so that you will be confident, yes, I understood this, I mastered this lecture. Okay, now that we have found M2R is an inner product space with a, okay, and what do I have? F is a bilinear map on M2R to R, namely f of A equal to determinant of A, and I know it's differentiable, therefore derivative of f at A is going to be a linear map from M2R to R. This is a linear map, right? But the Reyes representation theorem, what does it say? Any linear map phi from inner product space to R, assume this is a real inner product space, okay, and also finite dimensional inner product space over R. Okay, any linear map is of the form phi of x equal to x dot v, where for a unique v in capital V. Yeah, right? Therefore I can ask, this v is called the gradient. This is how we define. Please go back to my lectures on differential calculus. Okay, this v is called the gradient of phi, right? So my question now is, what is the gradient of dfa? Gradient of f at A, that is the vector corresponding to dfa. This corresponds to a vector, right? And this vector has to be a vector in M2R, but you can also think of it as a vector in R4, but I would like it to be an M2R as a matrix. Are you following? Yeah. Now let us look at, we already have found out dfa acting on H with the same notation. Let me just make sure. Yeah, I have to, yeah, AW minus CY, let me write it, plus B. I can do it again, but yeah, dx minus bz. So what is that I want? I want this to be of the form trace of, okay, how did we define dot product? We define this as H dot some matrix B transpose. Do you understand that? So I have to find what B transpose or B. Are you following? Then I will call this as the gradient. Okay, this BT is what I will call as a gradient. Are you following me? Sorry, B as a gradient. Okay, this is therefore this is H dot B. This B is called the gradient. Are you following what I am trying to do? This should be dot product with some vector. The dot product is defined as trace of H dot BT. That is H inner product is B. Therefore this B is called the gradient. So this B should be 2 by 2 matrix. But let's look at that. By inspection I can do that. This is my X, Y, Z, W. I want some matrix. This matrix is B transpose, which has 2, and it should come here. Therefore what should happen? Let's look at this. There is an X here, therefore the D should be here, dx minus Cx Cy, right? Therefore this must be minus C. Do you understand this? I would have got dx Cy. First row, first column. This must be the trace. Therefore first row by first column should be this. Let me use a different color. Okay, now I have to look at AW and BZ. That should be Z, it should be minus B. Therefore what should have? This should be second row by second column. Therefore what should happen? This is minus B and this should be W. So let us look at a different color scheme. This is going to be A. Therefore my B transpose is matrix. Therefore what is B? Therefore B is D A. I hope I wrote it correctly. Just make sure I wrote it. Okay. So since I wrote B transpose here, it's coming like that. It's all right, no problem. Okay. Yeah. Okay, let us do that. This is same as, let me write this, trace of B H transpose. So let us do that. You will see why I want. Okay, just bear with me for a minute. Okay, and notice this is B and this is X, Y, therefore Z, Y and W. This I want it to be the first row, first column. Therefore that should be something with A. That is going to be X is going to be D, and then Y is going to be C. Therefore A and minus C. X is D, sorry, D and minus C. Now I am going to get the same thing, yeah, naturally. Okay, and what should be the second one? Second one on to be ZW. ZW is going to be minus B and A. Okay, good. Yeah, this is my B transpose. Therefore B transpose is D A minus B minus C. How many of you recognize this? Yeah, this is what is called adjunct matrix of A. A is A, B, C, D, and what is it adjunct? It's not transpose, it's called adjunct matrix. Okay, in cofactor expansion of determinant, you would have come across adjunct matrix. Classically it's also called adjoint, but nowadays algebraists, okay, modern mathematicians try to avoid the word adjoint. Okay, they use the word adjunct matrix. So we found out the gradient. The gradient is essentially adjunct matrix. Yeah, do you follow that? Okay. Adjunct matrix of A. I put it in quotes because it's almost close to that, but for a slight change here. Okay, because B transpose is what you get, but I want a B. So if I put a transpose elsewhere, things might work, but let's not worry about. But if I understood this is good enough. So what is the next question? Okay, try to find analogues, okay, in MNR. This is again exploration, MNR. Okay, try to do that. That will again be easy if you have found this question. Yeah. Okay, for bilinear map we found out the derivative, then we found, okay, then can you do a multilinear map? Once I found the multilinear map, then I can do it for MNR also, determinant on MNR. Okay, right. So this more or less finishes what I wanted to do, but now I just want to have fun. See, the title is something to do with bilinear map and multilinear map and their differentiability, which you have done. At least for bilinearity we have done in complete thing. Not only that, we also found out, I can talk about the gradient, and we also found out the gradient. Okay, it's essentially, okay, it is the adjoint matrix. Okay, and if you want, you can also do it slightly differently. So if I, for example, if the inner product AB, if I define it as what, how did I define inner product? Let me just make sure. Yeah, so instead if I define it to be trace of AB to be B transpose A, okay, then you will see that it comes out with the adjoint matrix. The gradient will be actually adjunct matrix. Okay, don't get confused. Okay, so if A B inner product is trace of B transpose A, okay, I again get confused. Okay, which one of them? I did A transpose B, right? Yeah, it will follow. Anyway, let's not worry about. Now what I want to do is I just want to have some fun. So let's look at F from M to R, the determinant map. Right, now if I given any matrix A, instead of A B C D, let me write it as variable X Y Z W. Okay, then how many coordinates are there? A has 4 coordinates, namely X, Y, Z, W. Therefore what is F of A? F of A is X W minus Y Z, because determinant of that, right? Okay, therefore now this is a polynomial function. Therefore from algebra of differential function we know F is differentiable. Is it clear? Once if F is differentiable, then we know what is the gradient of F. Gradient of F is partial derivatives at the point, right? And not this F, in general. Yeah, very good. So now I can compute. Therefore what is the partial derivative of this map? This is W, del F by del Y is minus Z, del F by del Z is minus Y, del F by del W XX. Therefore I know the gradient, but remember the gradient I would like to write as a matrix rather than this way, not as an ordered quadruple. So what is the order I should write? The order should be del F by del x, del f by del y, del f by del z, del f by del w. But what is that? That is w minus z minus y and x. Yeah, that is reverting back to your ABCD notation, D minus C minus B and A. That's a gradient. Yeah, you follow that? So without any of this bilinearity etc., I could have simply computed this very easily. So what is the last question I should ask? Is there such a simpler easy method? Easy method to compute the gradient of what? To compute the gradient of determinant function on M and R. Right? I leave it to you with a hint. We saw the gradient turned out to be something to do with the adjunct matrix, and the cofactors are involved, right? You understand that? And the trick is to use the so-called Laplace expansion of a determinant. Okay, I'm not going to define what is it is. If A equal to Aij, okay, let Cij be the cofactor. That is cofactor, determinant of the cofactors. It's just a number for me. Okay, so I have Ij, this Ij, you remove these two things. Okay, whatever remain matrix, take it and take its determinant. That's what you call Cij, determinant of that matrix, not only the matrix. Sometimes cofactor only means the resultant matrix, but I also think of it as a determinant. So Laplace expansion says the following. What does it say? Ai1, or if you want xi1, okay, into ci1 plus xin into cin equal to determinant of A. Right? And notice that, and Cij does not involve, is independent of xij, because xij you removed from this, so that coordinate does not appear. You understand? Therefore if this is your f of A, you understand? Therefore del f by del xi j is easier to compute. It is just a Cij. Okay, I will more or less solve the problem. Okay, let us. So I more or less solved the problem. I hope you enjoyed, and do not get carried away by the inner product I defined M2R. It could be defined in many ways, so that you, if you want, the gradient could be actually adjunct matrix. Okay, I just wrote something A B transpose or something, so the gradient turned out to be the transpose of the adjunct matrix of A. But if I want actually the adjunct matrix of the gradient, you just have to simply manipulate the inner product. Okay, if not A B transpose A transpose B or one such thing, you just try it. Okay, that doesn't matter. The important lesson we have to learn is what, okay, we are done. I hope all of you enjoyed. Okay, we will come back later with something else. Take care, stay safe.